I want to thank everyone for coming. This turned out to be quite a large event. It was supposed to just initially be a little bit of training for a small number of people, but I'm really excited to see all the interest that we have. I want to start by thanking the people on my team that agreed to also give presentations today, taking time out of their own busy development schedules. And yeah, thanks to everyone that is attending. This will be good to get a lot of this information out there. So I don't have a set time agenda for this. I think there's a good chance it could run all day, but we may actually end a little bit early if things go really smoothly. So I'm going to kick things off with a overview of sort of starting with the big picture of Chrome OS firmware with all of the extra pieces, and then we're going to start drilling down into some of the specific components that make it what it is. We'll finish off the day with a little bit of talk about sort of how the Chromium process works for people that are going to be contributing, and some of the stuff to worry about for that kind of work. So to start with, I'm going to kick off with some overview of Chrome OS firmware, which is actually made up of a very large number of things. So I'm going to throw a whole bunch of different things at you. Largely, this is just to introduce the idea of what is in there. There's a lot more specifics available on the Chromium Wiki or in other places, and we are happy to take follow-up questions for some of these areas. But there will definitely be some stuff in here that doesn't feel like it relates, but it will start to make sense at some point if you actually are trying to figure out why your Chrome firmware isn't behaving as it should. First off, a big question we get all the time is, why are we so invested in the firmware that we do? Why do we care? Why are we not sort of out of this part of the game and just worried about shipping devices? So a number of us on this team came from the platforms organization inside of Google as well. And we are also very interested in sort of controlling the firmware in the server side of Google. And a lot of the reasons comes down to when we build our own platforms, or we are very involved in the development of a platform, we find it's very important to maintain the control over that platform, and you really can't do that unless you're starting at the firmware level. You don't, let's see, starting with Chrome OS in particular, we were deciding to do multiple architectures, and we really wanted a consistent set of features across multiple architectures. And at the time we kicked this off, there wasn't any common ground. Things are definitely moving in different directions. There is more convergence happening across x86 and ARM. That's a good thing for everyone. It's also important, if you understand the platform that you're working on, you can do a better job with your power and performance and deliver a nice product. And we all know that firmware is hard. It's guaranteed you're going to find bugs both in the firmware and in the hardware. And as most of us know, firmware is essentially a collection of workarounds for broken hardware. And for all of us, time is money, so shipping devices is important if you can hit these milestones, especially when you come up against back to school and Christmas time and all that stuff. And we also have a big focus on security. And when we kicked this off, there wasn't a lot of focus on security in the firmware side. And we found it was very important for us to be able to own the firmware piece so that we can ensure that security started at that very first instruction that's executed on a Chrome device. Before we get into too many details of the firmware itself, I want to talk about the Chrome OS boot modes, because this is sort of what lays the foundation for why we need so much customization inside of our firmware. The main thing you'll see with most Chromebooks when you power it on is that it's booting in verified mode. We also call this normal mode. In this mode, it can only boot Google-signed Chrome OS images. And it does a full verification of the firmware that it's going to execute, the read-write firmware, and the kernel that it executes off the disk. Verified mode does take a read-write firmware path, so we'll talk about this in a minute. We start in read-only code, but we do go through read-write code so that we can push updates out. And then in verified mode, we'll end up in recovery mode, which I'll talk about next, if a number of things go wrong. If any of the firmware that it's going to try and verify is corrupt, or if the kernel or the root file system is corrupt, or if there's a hardware failure that is sort of critical to ensuring that verification. Recovery mode is where you end up with the sad screen looking at you and says, you know, unable to boot, please go to this Chrome OS, I believe it's the web page that tells you how to download a recovery image so that you can boot and recover your system. Assuming it got there for not a critical hardware failure, you should just be able to recover and go back to how things were, but you know, obviously if the disk is actually gone bad, you're going to have a hard time still continuing to boot after you recover. So it can be initiated by the system itself if it detects a verification failure, but you can also initiate recovery mode for the user. We think it's very important for them to be able to ensure that for some reason if they feel their laptop has been tampered with, they can recover it back to what should be a good and verified and secure state. On the Chromebook devices, at least the modern Chromebook devices, this is actually done by pressing a sequence of keys, escape plus the refresh button plus the power button. This actually, these keys are actually hooked up to a little chip, a Sligo chip, that actually triggers a reset of all the devices in the system, so it ensures that the embedded controller and the host firmware all sort of start executing from their read-only code. And in the recovery mode, they actually stay in read-only code, so that we don't actually do any read-write code. So you can actually completely erase the read-write portion of the firmware chip, and you can still recover the system. The Chrome box, because we don't have a built-in keyboard, we don't have a way to do this same convenient keystroke method, we actually still have the physical recovery button that you hold down when you push the power button. Also very important to us is the concept of a developer mode. We really want people to be able to mess with their systems. It is nice for most people, and don't do this, but there is definitely hobbyists and hackers and our own developers that need to be able to get into the system. So it's built into every device. The early devices had a physical recovery switch that you actually had to, like this device here, it's in the key lock, and you had to stick a paper clip in and sort of flip the switch. We have now switched to a transition into developer mode that you get to by going to recovery mode first, and then you can hit the Control D sequence, which sort of says, bring me to developer mode, hit enter, and it will transition into developer mode. When this does happen, it erases the local state in the TPM immediately, and then you actually have to go through a Chrome OS boot where it'll erase all of the user state off the disk. This can actually make it very hard for debugging a system, but it's very important for security and for the user's privacy that if someone does take their device and flip it in developer mode, they have no way to get back to that data that used to be on there. And since it's just a cloud-based device, you know, all you do is log in again and all your stuff is synced down, so you're not really losing anything. Developer mode enables the root shell in Chrome OS, which allows you to start doing... Touch something. Crackling again. Sorry. It enables the root shell in Chrome OS, which allows you to start taking the system down in different pieces. You can turn off verification on the disk. You can allow yourself to boot USB sticks that might have your own signed kernels on them and stuff like that. There are some flags that can be set with a tool in Chrome OS that allow you to change some of the behaviors in developer mode. For a number of us, we like to have our devices in developer mode for flexibility and for debugging, but we also want to ensure that we're actually still only booting signed images from Google so that we can say the device is still somewhat secure. So there's a flag that we can set that allows us to ensure that we can't boot our own kernels, but we can still just boot the Google kernels. Another feature that isn't really a supported feature, but we've put it out there starting with the Chromebook Pixel, and there's a number of people, especially in the Linux community, that have found it very useful, is legacy mode. And this is a way to boot some other payload that would allow you to boot a different OS other than Chrome OS. Because our firmware is really just designed to boot our operating system only, it can be painful to try and get a generic Linux on there without this. People have certainly managed it, but you generally have to use the Google kernel, and it sort of you have to bend the Linux to work for you rather than the other way around. And for the Intel Haswell generation and the Pixel, this was the cBIOS project, which is an upstream legacy BIOS implementation. But this can actually be any payload. So there's going to be devices that the cBIOS doesn't support. And we haven't seen what people are putting in there yet, but this is just a region in the read-write flash that people can load anything they want into, and if they enable this mode, they can boot their own set of firmware there. So that's it from the overall view of what a Chrome OS device behaves like. Now I'm going to talk a little bit about the components that go into making up the actual Chrome OS firmware. So that's coreboot, which is the sort of the default BIOS environment. Depthcharge, which is our bootloader for Chrome OS. Verified boot, which is our sort of the security mechanism that I'll go into some detail about. and then the embedded controller, which we actually find is a very important piece for the overall firmware solution. I'm not really going to talk about vendor binaries, but they do exist. We sort of accept that they are a reality, as much as we would love to have a completely open source firmware. The world isn't there yet. So we do, have support for various types of different vendor binaries that we can integrate in different ways. So coreboot. Coreboot is what we have settled on for the sort of the base firmware that we use. It is a project that's been around since the late 90s. Ron Minnick is the guy that started this. Back then it was called Linux BIOS. Ron is over there in the corner if you want to ask him why it was called Linux BIOS to start with. Because it didn't actually involve Linux in the kernel and it wasn't really a complete BIOS, it got renamed to coreboot in about 2008 when Stefan Reinauer took over the project maintainer. Like any BIOS, it's made up of any modern BIOS, is made up of mostly C code, a little bit of assembly, and a lot of ACPI code. It uses a similar configuration mechanism to the Linux kernel. It's a kbuild and kconfig. It's slightly modified, so it doesn't behave exactly the same. I'll talk about that later. And it's also, the organization looks very similar to any other modern BIOS. It's sort of organized around the block diagram of the system that you might be working on. So, modular CPUs and chipsets and devices and things like that. Coreboot itself is not a bootloader. This is a strategic decision they made early on to not try and force one way of booting a system into the firmware. So it supports a number of different payloads, and those payloads can then boot different kinds of operating systems. And I'll talk about some of the payloads in a minute. The stages of coreboot, so when you first boot up, what is going on under the hood there, you start with the very early step of trying to get cache's RAM working and set up and make sure you can actually talk to your SPI chip and all the stuff you need is there. This is sort of called the boot block phase. It means a different thing on pretty much every system, the kind of work you need to do to get into the next stage. The main goal is to get some little thing you can use as a stack. On an Intel system, this means using the cache. On an ARM system, most people are lucky and have a nice SRAM. And then the next stage is the ROM stage, and this is where you are still executing code out of flash. And this is where you attempt to bring up the rest of memory and start some early chipset initialization that may be needed to support both bringing up memory and early access to devices. Once you have memory, you can start to do a lot more interesting things. You get to the point where you can load something from flash into RAM and start executing it there so you're not having to run from SPI. Start to enumerate devices, assign resources out, bring up all the other CPU cores, start creating the ACPI tables with stuff and install an SMM handler if needed, all that great stuff that you find in a typical BIOS. And then obviously the payload to actually boot something. For people familiar with EFI, it maps really well to the common EFI stages as well. There really isn't a lot of, there's not a lot of opportunity to diverge from this basic set of things when you're trying to boot a system. They all need to essentially do the same sort of things. So for people with EFI, here's the mapping. It looks pretty similar. So I mentioned that we have a payload concept. In order to support different kinds of payloads, there is a library inside of coreboot called libpayload. And it provides a set of common functions that a payload might need: access to devices, some drivers, a subset of libc for doing things like console output and standard math functions and things like that. There's a tiny ncurses implementation, which some payloads have used, but I haven't seen one recently that did a lot with it. And it can read and parse the coreboot table, which is a simplified table that is put in memory that contains some information about the system. libpayload itself is BSD licensed, and this was done for flexibility for people that may want to put in payloads or write a payload that was not GPL'd and would like to still release a firmware and sort of keep their payload private. And so that provides a little bit of flexibility for the different people out there. So, some of the common payloads that people use to boot stuff. Philo was an early payload. I don't know that it's maintained as much anymore, but it's really just there to boot the Linux kernel. And it doesn't have a lot of features or flexibility. It's there if you want a very quick firmware that all it does is load a Linux kernel and boot it. I mentioned CBIOS. This is a sort of a legacy BIOS replacement. It can boot Windows, DOS, things like that, which is great for testing. And it can boot all of the standard Linux distros without going through a lot of hooks. Depthcharge is the payload that we use that I'll talk about later, and it's really meant to be a verified bootloader for Chrome OS itself. There's also payloads. There's a Tiano core payload that someone's written. There's a number of other payloads out there. I didn't want to summarize all of them. So for how we work with the Upstream coreboot community, we typically we have a copy of the coreboot tree, the coreboot Upstream tree in the Chromium repo, and we try and rebase this regularly with Upstream. We typically try and do it after a product cycle, so after we've shipped for, say, for instance, the Haswell devices that we shipped this past year, we try and rebase with Upstream so that we can make sure that we're getting all the code that's going in Upstream, and we can push our patches Upstream as well around the same time. When that does happen, we will create a new Git branch in our local coreboot repo, and we'll sort of point the master at it. So the way our repo tool works is it sort of keeps track of what the current master is pointing at, so we can just point it at the new one, and the old one sticks around for all the other boards that are still there in case we need to get back to it for some specific reason. And then we do push our patches upstream. We find this is very important. We'd like to, it's not something we're required to do, but we really want to be a good community member, and we would like to be able to continue using the upstream version of coreboot where possible. And it makes it easy for the sort of the hobbyists and the hackers out there that might want to go upstream and download a firmware and play with it on their own device. The upstream coreboot uses Gerrit for patches and code reviews, and it's Git-based, so it actually is very similar to the way the Chromium workflow works, which will be talked about later today as well. So as I mentioned, Depthcharge, this is the Chromium specific bootloader. It's a payload we designed that really is only there to boot Chrome OS and integrate with our verified boot implementation. It's very streamlined. It doesn't boot other operating systems. It can, however, chain to another payload that you could use to boot something else. So that's how we can have this legacy mode where we can boot CBIOS and allow people to boot a different operating system. And we have a session on Depthcharge later today as well. So okay, now to go into verified boot. This is sort of the, I guess it's one of the first things that the Chromium team came up with when looking at Chrome OS, and it was their solution for how to ensure that we're always executing Google signed code on a system. And the way that starts is that the root of trust in the system actually needs to come from read-only firmware. The only way that we can be sure that we're guaranteeing that someone's not running a modified image is that they have a key that's read out of some hardware-protected read-only firmware that is then used to verify all the other stages of the boot. And so that does put an extra barrier between a user trying to completely sort of own their system and put their own firmware on. They actually have to open the device up and generally take a screw out or something that is forcing that write protect. And in doing so, they void their warranty. So it's kind of, you know, good and bad depending on your perspective, I guess. So this read-only firmware that comes up, its job is to get things far enough up that it can have enough resources to verify a read-write firmware. So the goal is to try and push this barrier of how much read-only code we have to be as small as possible, because obviously that code has to sort of work perfectly. And so we're trying to push that earlier and earlier into the boot process. And once we have verified some signed read-write firmware off the disk, we jump to that. And its goal is to get the system up and to get to the point where the read-write firmware can then verify a kernel off the disk and boot it. And one of the first pieces of code that was written for the Chromium OS project was this vboot reference, and this is sort of the library that provides the vboot infrastructure. And that's available on the, I think it's a BSD license, or Apache. I should know that. So then the next piece is the kernel, and this is how we sort of pass that root of trust up to the operating system, and once firmware is done, we try and get out of the way, but we still want to ensure that the kernel that has been loaded and is booted is still working on signed code, and can't really be easily modified. So the file system, the root file system on a Chrome OS device that's booted is actually a read-only image. It's not read-only at the hardware level, it's sort of read-only at the kernel level, which means that, you know, enough access into the kernel and you can set things up differently and reboot the system, and you actually turn off that read-only and you can start to make changes in your root file system. And there is a script when you get in developer mode you can run. I believe it's called make dev SSD, and it will basically re-sign your kernel partition and turn off this read-only verified mode, and you can actually mount it and make changes to it. But of course you can't go back without recovering, because once you've made changes you won't have the key to re-sign your root file system. So the way we do this is that we hash every block in the image. When we create a Chrome OS image for distribution, we take that image and every block is then hashed. The block hashes are bundled together and structured into a tree format based on sort of when the blocks are going to be accessed. So we can profile the boot and determine that you know, we're going to need these blocks first, and so those get put higher up in the tree. And then the hash of that very first block at the top of the tree is stored with the kernel and actually signed and passed to the kernel on the command line. So the command line that's used to boot the kernel is actually signed with the kernel, so you can't modify the command line without also re-signing your image, so that you can't, you know, disable your verified boot mode without having to also re-sign your kernel. And then when you, after that first hash is passed in, it reads the first blocks, and subsequent blocks are read out of the tree. They actually get stored in the page cache, so you don't really need to verify every block again unless things start getting flushed out of the cache. So the upstream, the kernel implementation for this is called Verity. It's a device mapper implementation in the kernel, and sort of this is what I was talking about for how the blocks are arranged and hashed. This is a very simple example, obviously. You know, 32K blocks, and there's only two levels of hashes needed if we have 128 hashes in a block size. And then you have that root hash at the top that is then passed down with the kernel as it boots. And Verity is it's a transparent block device implemented in the device mapper subsystem in the kernel. And it's a driver that we wrote and upstreamed with the help of Red Hat. And so it's upstream in the Linux kernel, and it's actually now an experimental feature in Android as well. We're looking at trying to get more and more people using this system to ensure that they're running off of a verified file system. I don't believe anyone's using it yet on Android, but it is definitely there, and I suspect it will start to get more use in the future. So I've mentioned verified boot, I've mentioned how it boots through things, but to try and give a little bit of a diagram for how it works, obviously I said we have the read-only bit of code that does this sort of verified boot firmware stage, we call it. And for the standard device, it picks between a verified mode or going to recovery mode if the user requested it, or if for some reason some device failed and it rebooted to recovery mode. In the verified mode side, there are actually 2 copies of the read-write firmware in there, and this is pretty standard for updates, is to be able to, you know, push one copy, make sure you can boot into it before you update the other copy. And then the same sort of selection of an A and B happens when you're booting the kernel as well. So there's actually many different paths you could take to get into the image, but in the end you should end up in the same place. And then if for some reason you go to recovery mode, it stays in read-only code in recovery mode, and it boots a verified boot kernel that only allows you to boot off of a removable device. I say USB down here, but it actually also includes SD cards and things like that that aren't connected via USB. And you can only boot a recovery signed kernel image in this case. And the recovery image is just a, you know, scripted version of Linux that will go and completely wipe what's on your disk, wipe your TPM, reinstall Chrome OS, re-flash the firmware in the read-write portions, and basically try and return your device to a standard verified Chrome OS device. Developer mode obviously complicates things quite a bit, so I kind of split that out separately. By default, developer mode, when you boot it, it'll wipe your disk, wipe your TPM, but it doesn't actually change the behavior of how you can boot the system, other than you get a big scary warning screen when you boot. In order to start changing things, you have to set some flags in the system, and the first flag you can set is a flag that lets you boot off of, it says USB again, but it lets you boot off of removable media. And so by default, you'll come up and you can boot off of the SSD only. You can, however, put your own signed images, they're sort of unverified images, on the kernel or on the SSD and boot them without having to set any flags. But if you do want to boot off USB, you have to set a flag, and then you can boot your own kernels off of USB. And as I mentioned, there are definitely some people that are interested in running in developer mode, but also still trying to be as secure as possible. So there's a flag that can be set that forces you to boot only Google verified images. But if you want to start experimenting, you definitely don't have to set that flag, and you can start to boot your own kernels. So how does verified boot integrate with the firmware itself? I had mentioned the firmware boot stages earlier. Reset vector comes out, we go into the coreboot ROM stage, and then we execute the verified boot firmware side of the implementation, and this is all still within read-only code. Then we jump to a read-write version of RAM stage that then goes into Depthcharge and executes the kernel side, and then we finally jump to a kernel. So it integrates pretty cleanly with pretty much any firmware implementation. It's just finding the right points to hook in to make it work. Yeah. So that's it for coreboot for the moment. I'll get into that a lot more. in a second, but for now I'm going to talk about some other pieces. The embedded controller. So we definitely found that, as everyone knows, the embedded controller is responsible for all sorts of very required things, but also can be in the way if it's not something that you control. Early on, we found that embedded controllers were not really paying a lot of attention to security, and they were vital to the system, yet they were completely closed off. They were closed source. We had no visibility into both how they were behaving for debugging, but also, we had no way of knowing if for some reason that embedded controller had been, had been hacked. And, since it is the keyboard for most laptop devices, it could be a keylogger or it could be inputting keystrokes. So for us, it became important for security to actually own the embedded controller as well. So we implemented an embedded controller firmware that is completely open source. And it's designed around security and, obviously simplicity. And it follows a lot of the same sort of design decisions that we did for the firmware itself, in that it has a read-only and a read-write regions. I believe it only has one read-write region. Bill will correct me later if I'm wrong. And that read-write update is actually signed and passed down by the firmware at boot time. So if a new embedded controller is released and it's pushed out in an image, it'll be flashed into the host firmware. And when the system reboots, it'll actually ask the embedded controller what its hash is of its current firmware. If it's out of date, it'll flash the new firmware and move on. Bill will talk about this a lot more later. So this is called EC Software Sync, is our name for it. And at the moment, the only sort of embedded controller SoCs that we claim to support are the TI Stellaris and the STMicro STM32 parts. We're definitely working on more of these. We'd like to have a lot more embedded controller options out there. Okay, so now that I've talked about sort of the main components, I'm going to talk about some of the support infrastructure that's in place that makes a Chrome OS firmware image sort of come together. And so I'll go through each of these in some detail here. The flash map. Now this is something that pretty much any firmware that's out there that needs to describe different regions has a concept of mapping their flash out. Flash map is a very simple specification that we actually developed in the platforms group at Google for the data center firmwares we were working on. So we've used it in legacy BIOSes and UEFI implementations, and then coreboot and the embedded controllers use it. So it's just a very simple specification for describing how a flash is partitioned out. And as we were able to sort of open source the design and the implementation, and we decided to then make use of it in Chrome OS. And so it's a very simple structure that you find a header. It's 64-byte aligned, I believe, in the flash. And from there, you can basically very easily figure out what the regions are that are in the firmware. And it's sort of self-describing in that way, which can be really nice for tools to be able to take advantage of it. So we've integrated flash map into a number of different pieces of the firmware. So if we look at this is a Chrome OS firmware image from I believe I took this from a PEPI device, which is the Acer C720 that came out. And this is what the flash map actually looks like. So given the same read-only, read-write split here at the bottom 2 megabytes are hardware write protected, so they are read-only. And then the top 6 megabytes are actually, or I guess, sorry, the bottom 6 megabytes, depending on how you look at it, are read-write. In practice, however, the Intel flash descriptor and the memory and the management engine are also read-only. They're just not read-only at the hardware level. They're sort of read-only from the SPI controller level. So really that bottom 2 megabytes is lost as well. So then we split up things. Excuse me. We have 2 copies of the read-write firmware that might be executed. We have a copy of some memory training data that gets saved to assist with fast boots and resumes. We have some event log information, which we'll talk about later. VPD information, which I'll also talk about, and then there's that big legacy region, which we actually, because we have 8 meg SPI parts on these things, we ended up with a decent amount of extra space, so we carved out 2 megabytes for this legacy region for people to be able to put whatever they wanted in there. And then the read-only side as well, some copies of product data as well. The FMAP itself actually lives in the read-only portion of Flash so that it can't be changed. And then this Google binary block, which I'll talk about in detail in a minute. And then at the bottom here is our actual read-only firmware in this boot stub region. So boot stub is kind of special in that it contains the reset vector. So all the, whenever the system's reset and it comes up, that first bit of code is going to be out of this boot stub section. So every boot will execute coreboot ROM stage and the verify boot firmware side of the picture from this boot stub section. And then if you're in recovery mode and you're sticking with read-only firmware to do a recovery of the system, we stay in the boot stub section. It actually contains a full copy of the coreboot RAM stage, Depthcharge, and the VBoot kernel implementation. The one thing about this is that this read-only firmware it will only boot off of a signed signed removable storage, so USB, but also SD cards that are not attached over USB. And this is to ensure that no one in recovery mode can also boot off of the disk. They can only boot a signed Google image for recovering the system. Within the 2 copies of the read-write firmware that we have in the flash, we break it down into the A and B areas, but each of those is broken down into a region that stores the key blocks and the information about the signing. There's a copy of the BIOS, there's a copy of the embedded controller, and then there's a tiny block at the end that contains the actual firmware ID for this new firmware version. And this is where I was going to point out that the EC is also bundled with the firmware, so it gets put in this special section and sent down to the embedded controller at boot time. The way we build the flash map, now there's obviously any number of solutions to this. For various legacy reasons, we actually use a flattened device tree format, and there's a number of different sort of custom things we've put into the sections to describe the signing. And really what this is here is meant to be an input to a tool that then sort of constructs the final flash image out of all these various pieces and does the signing and makes sure they go into the right areas. So it really looks pretty ugly, but on the surface, it's just describing the same flash map region that we talked about earlier. The V block has all the key information, and then the firmware actually lives in there, and the EC. So outside of the flash map, there's also the disk map, and for this, we did need also some custom stuff because we needed to support very convenient access to the kernels without having to talk to a file system. So the kernel is actually signed and stored in a raw partition on the disk, so it can be easily read out without having to sort of interpret a file system and worry about any security holes that may be in the implementation of sort of traversing that file system. And then we also have multiple copies of the root file system in there as well. So when an update happens, it updates the copy that you're not running from and tries to boot into it. And if it succeeds, it'll then be in that new version. If it fails, it'll actually be able to fall back to the old version. To support that concept, we added some custom attributes to the GPT table. So we have a priority field that basically tells the VBoot kernel implementation which of these partitions it should try and boot first. We have a try count, so if we did update to a new Chrome OS image in, say, section B, we set the try count up and we set its priority up, and it will try and boot that new image a number of times before it eventually will give up and it'll just go back to the old image. If it's successful in booting, I think it's about 30 seconds after boot, there's a script that runs that I believe is called Chrome OS set good kernel, and it basically just goes and sets this GPT flag that says, we've successfully booted into this new image, you can consider me good from now. And we wrote a tool for modifying these GPT flags, especially these custom ones called CGPT that's you'll find it in a Chrome OS, on every Chrome OS device, but also within the chroot that is created for the Chrome build system. There's only one partition in the entire image that has read-write data, and that's for the user data as well as the stuff that lives in bar log, and I believe as well user local may be in there as well. And anything that's user data, and I believe the log stuff is actually encrypted, mounted with an encrypted file system. And so if we look at what the image looks like, that read-write information is at the top here. That gets sort of mounted by default in mount stateful partition, but then all of the user data for users that have actually created an account on the system are encrypted files within there that are then mapped separately when the user logs in. We actually have 3 copies of kernel and root file systems in there, although we don't use the 3rd copy. It's sort of there for potential future use or other interesting things that people may want to do. Before we had legacy firmware, I think people were shoving their own root file system and kernel C and setting flags and sort of booting Linux that way. And then they could boot back to Chrome OS just by setting flags and rebooting. There's an OEM partition at the bottom that is available for customization. I believe the Pixel used this, where it came with a high-resolution movie that sort of showed off the fancy screen. And And then we actually have a read-write firmware partition. We haven't really made use of this yet, but one of the ideas was that we could actually put the read-write firmware on the disk rather than in flash. This is something we've experimented with, but we haven't really been happy enough with the results, and the security people have some concerns about it, so we really haven't gone down this path yet. And then we also have an UEFI system partition at the end for being able to boot, the images that we create on generic systems that run EFI. So I've mentioned that we have a TPM. A lot of people aren't aware what we use it for. We don't actually use the TPM in the traditional way that a lot of firmwares that sort of do a trusted boot might use it. We don't use it for cryptographic functions. It's a little too slow for that. Mostly we use it to prevent rollback attacks. So we store some version numbers for the keys in the NVRAM of the TPM, and then those version numbers are read out by vboot and compared against the current key that things are signed with. So if we increment key versions, you can't sort of attack the system by trying to put an old firmware on there, because once the TPM has been advanced to the new version, it will no longer boot that old firmware or that old kernel. And then once we moved the sort of the away from the physical developer switch, we also started storing some of the state of the system, of whether you're in developer mode or in recovery mode, in the TPM. So we have PCR0 is extended, and it sort of contains just a few flags that say whether you're in developer mode or recovery mode. The TPM is locked in the firmware unless you're booting in recovery mode and you need to recover things. You need to actually, recovery system needs to be able to wipe the TPM as well. And we also disable physical presence in the read-write firmware before we get to the kernel booting stage. And the drivers for the actual TPMs are in coreboot and Depthcharge, and this is for standard LPC TPMs as well as some I2C TPMs, and we're looking at obviously SPI and stuff like that. So the drivers are there in coreboot and Depthcharge, but really the interface to the TPM is driven by verify boot. The drivers may do may call some of the init functions by themselves. So in the verified boot firmware side of the story, we really only execute a few of these functions to the TPM, initialize, start it up, say that we're present, read the value out to check the firmware key version, ensure we can boot the firmware that's been updated on the system. And then we set the global lock bit, unless of course we're in recovery mode, extend that PCR0 and figure out if we're in developer mode or in recovery mode at this point. Okay, can you hear me? Nope. Try again? No? Hello, can you hear me now? Yep, sounds better. And then in the verify boot kernel half of the picture, we do even sort of less with the DPM. We read the NVRAM again and check the kernel key version to ensure that the kernel keys have not been rotated and that we're not trying to fall back to an old version. Extend the PCR again to check which mode we're in. If we are changing modes, for example, if you're transitioning into developer mode, we actually write this PCR back out with the new boot mode state. And then we lock physical presence in the TPM and boot the system. Okay, so this I had mentioned before but didn't give any detail, the Google binary block. This is really just we had a variety of things that we needed to store in the firmware for the system that we just needed a very simple way to describe them. So this is all stuff that needs to be in the read-only firmware. And it contains things like the hardware ID for the device, which I'll talk about in more detail, flags that can affect the boot of the device, the bitmaps that show up on the screens for the different firmware schemes, and the actual root keys and recovery keys that are used in the system. So this is where the actual root of trust is stored. So the hardware ID, this is something that allows each system to be sort of uniquely identified. It's not a new concept. Basically, we take various information about the system during the factory time. Some of it's including the build phase, if we're in EVT or DVT, the read-only firmware version, and then sort of a catalog of all of the hardware and firmware components that have been that have been found during the build process. Sometimes this will be just read from the device. Sometimes it requires the operator at the factory line to sort of scan something to say what's actually being put into the device. During the factory, if for some reason a new component slipped into the build, this would cause sort of a new hardware ID be generated that would not be in the approved table, and so it would flag that system, and you know, the operators would come and take a look and figure out why that hardware ID didn't seem to match up. So this tries to help us catch things like even a new trackpad firmware version or something that might slip into the build without us being aware of it, so that we know about things that change in the system. And then it also allows us to uniquely identify the different hardware that is out there, so we can do metrics, we can send the right recovery images to people, and make sure that updates are sent to the right types of devices. Sometimes we may not update one device to a new Chrome OS release yet because there was some problem found during testing, and so we'll hold it back based on the hardware ID. And because that hardware ID lives in the firmware image, and you can build your own firmware images, when you actually build a firmware image yourself, you're going to get a hardware ID bundled into your firmware that actually is just a test hardware ID, so it doesn't actually describe the hardware you're on, which means if you take that raw firmware image and just straight flash it to the device, you're going to lose your original hardware ID, which will make you fall out of updates and things like that. So the firmware update scripts that I'll talk about in a second sort of preserve that original hardware ID and make sure that it doesn't get lost when we update the firmware. Unfortunately, these hardware ID bundles for all the various systems, they live in an internal Git repository at Google. Some of this is because we don't really want to leak new devices and the components that are in them. And so, you know, the factory bundle that's provided when a factory's image is released does contain the hardware ID bundle for that device, but people can't go and browse all the different hardware ID bundles that are out there. The bitmaps. So the various firmware screens that can be displayed, including the sad face because you couldn't boot the system and you're going to recovery mode, the warning screens that you're in developer mode, and the transitional screens back and forth. Those all live in this binary block as well and are read-only. These are constructed with layers of images and text, and the text is all localized, and the images are sort of compressed bitmaps because we found that got the smallest. This is a bit of a challenge to scale to every possible locale out there, and we're sort of trying to work out some ways now to figure out how we can squeeze more information into this region. When you do boot up a system and it shows you that screen, you can actually use arrow keys to switch back and forth, and there's a way to set what the default locale is, but if for some reason you bought a device in a foreign country and you couldn't speak the language, you can still get back to English. But because it's all stuff that it needs to be available for recovery mode, these all need to be in the read-only part of the flash. So the firmware keys. So this is, as I said, where the root of trust begins. We actually use a combination of public key and cryptographic signatures, so public key, cryptographic signatures. The private keys are generated at Google. They're only known to Google. They're kept on a special server, hopefully in a locked room somewhere. I don't know the details. And then the public keys are the ones that are stored in the Google binary block and used to verify the images that are signed with the private keys. The data itself, except for the user data on the system, the data at the firmware side especially isn't encrypted, it's just hashed. It's used for signing and verifying. We're not actually trying to decrypt something on the fly. The root and the recovery keys are very large. They're 8K RSA keys with SHA-512. This is because these are baked into read-only firmware. We have no chance to update these keys. We don't want to have to deal with a situation where for some reason this key was compromised, and making them this large gives us a little more sort of flexibility in that area. The subsequent keys, the sub-keys that are used to actually verify different parts of the system may actually be smaller, and they actually are smaller. And each of these signing keys is also versioned, and that's where we have the versions that are stored in the TPM, and we can reject lower versions if for some reason that key was compromised. So there's also a set of flags. It's just a simple 32-bit variable in the binary block here that sets some flags that can affect how the boot of the device works. Largely this is used to drive the factory process. That's sort of where this initially came from. In the factory they need to boot off USB. They need to be able to be in developer mode. They had some requirements that made it so that a normally booting verified system didn't work very well in the factory. They actually turned out to be pretty useful for developers as well. There is definitely some stuff in here that can be very useful for the device you're working on. as Bill will talk about later, this EC software sync, if you're working on the EC and you're trying to put your own EC image on there, and then you boot a firmware, it's going to sync down its own version of the EC that it has in there, which can be very annoying if you're trying to actually put a new firmware on the EC. So you can actually disable that mode. You can set flags that force you into developer mode. You can set flags that force you into a legacy boot mode. And you can also disable the firmware rollback checks if you're also trying to work on firmware and your TPM has advanced and your version that you're building for firmware has not. To work with these flags, there's a tool called GBB utility that's present on the Chrome OS image itself, but is also found in the chroot for a Chrome build system. And it actually allows you to change all of the different pieces in the GBB that I've talked about. The common stuff that people do with it, though, is usually just to read the hardware ID or to set and get the flags that have been set for the device. So a quick example here of how it works. You read out the image with flashrom. You have your BIOS image then. Use the GBB utility. You can read out the hardware ID there. This was from a PEPI device. You can see that by default the flags were 0, but I'm going to set the factory flags, which is 39, which I believe, based on this thing, switches. I believe it makes it the short developer screen delay, forces the developer mode, and also allows to boot off USB by default. So flags that are very interesting for the factory. And then you write that new image back out to the system. And using the flash map that's integrated with flashrom, you can just write that GBB region. So to make this even easier for users, we have a script in the image called set GBB flags, and you just give it your new flags, and it'll sort of do that set of processes of reading out, changing the flags, and writing it back out. And so that's that if a user, if all they want to do is force developer mode and a short screen on their device, they can just run this script and after they've defeated write protect, of course, and not have to worry about the details. Another thing that's important for the firmware is that there is the ability to store some device-specific information into the firmware. And obviously the serial number is pretty common ID. In the Intel world, these are usually FRUs. FRU stuff, and we just sort of defined a vital product data structure. We have a copy of this vital product data in both the read-only and the read-write versions of firmware. So some of them are sort of set by the factory and baked in. Others can be changed. Like if you activate the system, it will store that in the read-write VPD region. And there's also registration codes for the devices that come with 100 gigabytes of Google Drive or something. When you go activate that, it'll write this key into your firmware and sort of know that you've activated it for this device. So there's a VPD tool that is used to work with these regions, and it can work on both the read-only and the read-write. It operates on an image, or it operates on the flash itself. And so just an example here, dumping out what's in the read-only. You can erase and reformat, add a new serial number, write it back out. The common stuff you'd expect if you were going to actually work with that stuff. So the update process. I'd mentioned that the update process does have to do a few things special. Obviously, the fact that we only try and update the read-write portions of the flash and that we only try and do half of it at a time means that it has to be a set of various scripts as well as the images. And so we end up sort of combining all of the images, the utilities to work with those images, and the scripts that actually do the work into a shell archive. So all you download is this, all you get is this image that's called, or this file that's called chromeos-firmwareupdate. And if you look at it, it's got some shell script stuff at the top, and then it's got a big blob of compressed image in there that it can sort of decompress itself. And so the biggest piece of this is flashrom that I mentioned before. This is an open source flash chip programmer that's been alive for a very long time. We've made a number of customizations to it to integrate FMAP because that becomes very important for us for working with individual regions. We also do some different flashing that people may not in a normal system. We like to use FTDI for our debug interface. We can support DediProgs. And there's also integration with actually being able to write a number of embedded controllers through a SPI pass-through interface with flashrom. And not mentioned here is we do have a utility as well for working with the EM100, which is a SPI emulator from DediProg as well, that we find very useful for development. So yeah, I mentioned this before. To actually do an update on the system, you sort of set one version, you try and boot into it the same way the kernel works. So you set a You flash region B with flashrom, and you set a flag that says try and boot region B, reboot the system, and it'll try and verify and boot into that newly flashed firmware image. If it comes up, you can see that it, with cross system, which is a tool I'll talk about in a second, you can see that it booted out of firmware B, and you can see that it's running that new version that you expected it to flash. And you can say, okay, that's good, now flash section A, and it'll flash the new section, and you reboot again. And because that flag had only a try count of 1, it's been decremented to 0, it's going to now boot out of section A again, and you can check and see that section A now also contains the new version of the flash. So pretty straightforward. This is a concept that's been around in different BIOSes for quite a while. I had mentioned the cross-system tool. This is a tool that we wrote that really is designed to interact with verified boot. It does do some system-related stuff, but its real main goal is to talk to verified boot and be able to configure it, be able to read state and information out of it. If you run it by default, you'll get a very long list of keys and values. A number of these, the ones that say writable, can actually be set with cross-system. So this is where you set things like dev boot USB if you want to be able to boot a USB image in developer mode on the system. On an x86 device, many of these flags reside in CMOS. On an ARM device, they reside in a different NVRAM region. Go to the next one. Another tool that you'll run into if you're working with our devices is Moses. This is just a simplified firmware and hardware sort of interaction utility. This was spawned from an internal project that we did in platforms as well that we called GSys. We open sourced a version of it and sort of continued using that in Chrome OS. The main thing that we use it for, that I use it for especially, is the event log, which I'll talk about, I believe, next. And the event log is very useful for debugging a system, especially when it's in verified mode and you have no way to actually get in and look and see what's actually going on in that system. So if a user files feedback with Chrome OS, which I think is Control-Alt-I or something, Alt-Shift-I, we'll actually read that event log and it'll be submitted with the feedback that they send. So if they say, my system is behaving weirdly, and they generate feedback, we can see from that feedback what happened in the system. When did they boot? When did they go to sleep and wake up, and that kind of stuff. And I'll talk about that more in a minute. Okay, so that was it for the overall view of sort of Chrome OS firmware in general. Now I'm going to talk a little bit about coreboot specifically and some of the features that are in coreboot, some of the stuff we've added, and some of the stuff you might run into if you're actually looking at coreboot source. We'll get into a lot more detail about sort of porting coreboot to different chipsets and mainboards in future sessions here. So the first thing you'll notice if you're looking at the coreboot source is that it looks a lot like the Linux kernel source. It really uses essentially the same coding style that the Linux kernel does. I believe there have been some slight modifications. Not everyone agrees. It's pretty much impossible for everyone to agree on a coding style. But the basics are still there, 80-column line limit, and 8-character tabs, and all that good stuff that you'll find in the Linux kernel. And this is good because it keeps consistency for people that are working on both of these things at the same time. So a lot of us on the firmware team also do kernel work in different areas, and it just makes it easier if we can all keep to the same coding style. As I said, the configuration is a version of kconfig and kbuild. The big difference from what the kernel uses in these areas is that the config options that you might define in your .config, which is make menu config or whatever to configure it, they're actually always defined. So that means you don't want to use ifdef to try and check if something's defined. You want to use #if. So the flags that are turned off, they're actually going to be defined as 0, and the flags that are turned off will be defined as 1. I'm sure there's a historical reason why this was done. I actually don't know it. We can ask Stefan or Ron later. It does allow you to use more than just the macro constructs for #if. You can actually use the configuration options inside of a regular if statement. So it is convenient in some areas. That said, there are some defines that you will see that are sort of used to differentiate different build time things. There is some files that are attempted to be reused both in ROM stage and RAM stage sides of coreboot, and in doing so they may have subtle differences in how they need to behave. So there is this pre-RAM define that you can use that you can tell that code is going to be executing in ROM stage, and if it's not pre-RAM, it's going to be executing in RAM stage. And as well, for system management mode, there is some stuff that is sort of reused in system management mode, and we want to sort of, it may have different requirements or access methods it needs to use. Some of the header files in particular are included in the ACPI, are sort of ran through the preprocessor included with ACPI so that we can reuse some defines from header files. That may then need protected so that the functions that actually are defined in header files aren't passed to the ASL compiler. And there isn't a lot of assembler code in coreboot, but there is some, and it sometimes may be mixed in, and you'll see it guarded with the assembler directive. ROMCC is something I'm not really going to talk about much, but it's a boot block compiler that we can use to compile C code before we have a stack. It tries to take advantage of the registers in the CPU to provide things like function calls. It's a very limited compiler. We're trying to limit its use as much as possible. Looking at coreboot, if you open it up and you look inside, you'll see a couple of top-level directories. Of course, the interesting one is source, because we all like the source. It's fairly self-describing. There isn't a lot to say about the directories you'll find in here. Most of it sort of describes itself, embedded controllers. You'll find all the different components you might find in different motherboards. Coreboot does have a, does go back a decent ways, and so you're going to find things that aren't as relevant in today's world, especially with mobile devices like Super IOs and things like that. And then there's some vendor-specific code. Largely that includes AMD has open sourced their GISA framework for various chipsets, and that's included here. And the Chrome OS Support code is also in the vendor code directory. So when you take these pieces and you integrate them, or you're trying to sort of define a new mainboard, you may integrate from different sort of supported components. So like the PEPU project has a Haswell CPU, Haswell North Bridge, it has a Lynx Point South Bridge, and a Chrome EC. And so it'll define and include pieces from all these other different areas of the source. The Bailey Bay Bay Trail reference board is SoC, so we have that Bay Trail support in SoC/Intel/Bay Trail. And for example, the Snow motherboard, which is actually the Samsung ARM Chromebook, we did a port to coreboot to this project. It didn't ship with coreboot, it shipped with U-boot, but we did an early port to this project, and it's in the SoC directory for that Exynos chip. Okay, so getting console output inside of coreboot, again, looks fairly similar to the kernel. We have various log levels defined that are pretty common. You can actually configure in the configuration system, you can set the maximum console log level, so anything that's above that in a message will get compiled out. And then you can set the default log level, and you can actually, if enabled, you can change that log level that is used in CMOS or something that allows you to then see more messages if you're trying to debug. And as a simple example, print K, a BIOS info level, and a message. The main difference here to the kernel is obviously the BIOS info prefix instead of kern info, and the fact that there's a comma instead of just a space. I think it's just a difference in the print K implementation. A relatively new feature in coreboot that isn't fully upstreamed yet is a data-driven process for initializing devices. A lot of times we run into stuff where we have a big list of registers and a big list of values that need to be written into those registers. And for many years, this has sort of been open-coded inside of functions where it says, all right, read out this register and these bits, or these bits, and write it back out to the same register. We decided to sort of simplify this and pull it into something that allows you to script this behavior, and it sort of keeps the code size down and makes it easier to parse and read and figure out what's actually being done. So you'll see a lot of this in the Bay Trail implementations where we started using it first. But we're going to probably see more of this in the future as we do different chips. It supports a number of different I/O interfaces, the common ones you'll see, and it can maintain the context of the device. And I'll talk more about the device structure in a minute here. But you can say run this register script on this device, and then you can actually just talk to that device as if it was part of the register script without having to pass it in every time. And you can chain different scripts. So you can actually build up a chain of different scripts that run and initialize something. A very simple example for how this works, this is a function to reset a USB 3 port, passes in the device for that USB controller and the port number that you want to reset, and this will issue the worm reset to the bar within that device, wait for up to 100 milliseconds for it to complete, and then clear the status bits and sort of move on. And this is then use the red script run on device to say run on this particular controller and use this script. So the devices. This will get talked about more in different sessions as well. I'm going to kind of try and give an intro here, but you'll hear about it more from Aaron and Sean later. So coreboot, in addition to the kconfig, it also has a concept of platform-specific configuration settings. This is stored in the mainboard file, or in the mainboard directory, in a file called devicetree.cb. Once again, this has no relation to Open Firmware Device Tree or Flattened Device Tree or anything like that. It was a coreboot-specific implementation. It has its own, lex yak parser in util sconfig. That parser sort of reads out what is in this device tree. It does some translation of path names into sort of variable names, and it sort of creates some magic variables that you can then use to access some of the device that might be used to configure the system. So as an example here, once again going with Peppy, this is a snippet of what its device tree may look like. So it's trying to describe the overall chip that's in the system, that it's a Haswell Northbridge, it's got a Haswell CPU in there. Some of these things are legacy that don't make a lot of sense in today's modern CPUs, but sort of the same constructs and abstractions are used. The interesting thing that I'm pointing out in this example that I'll show in the next slide is that we may have a configuration option for the SATA port map. So for Peppy, we have one SATA port. We don't need to enable all the other SATA ports. So we set, a flag or a value here of hex 1. So we're just enabling the bottom port. And then a device describing the actual SATA controller there. And so to actually make use of this, when the firmware is compiled, it will take that information from the device tree and create some structures and sort of a tree of these devices that you can then find within coreboot. So I'm going to highlight and try and show how that SATA port map actually gets written out to the device. Another magic file that lives in each of the chip directories is this chip.h, and it can be used to describe the configuration options that are available for that chip. So this SATA port map is a configuration option available for the Lynx Point Southbridge, and it gets consumed by the SATA device. For the overall chip for this Southbridge, it's defined here in pch.c. It can have an enable device, which obviously you can see there does nothing, but could be used if you wanted to actually turn on a device. So this enable dev will get called for each device that is found under this Lynx Point Southbridge chip. And then inside the SATA file itself, we may have an initialization function that finds that configuration structure, pulls out this SATA port map variable, and writes it out to some magic register there in the Southbridge, or in the SATA controller. And because this SATA device is a PCI device, it'll have some sort of basic device operation set that we can, for the most part, just use the common PCI device operations for, and define its init function, and then create a driver structure that sort of describes it and makes it and sort of binds it to the device that might be discovered at boot. So in this case, Intel vendor ID, the device ID for Lynx Point. In this case, I simplified it to just the AHCI version of that device. So this is used in a number of the RAM stage drivers and devices that you'll see if you're looking at the coreboot source. It does take a bit of, it does have a bit of magic that happens behind the scenes, and so it's definitely trying to point out that there is things that is created based on how it is listed in the device tree and how it's arranged on the file system. So Aaron and Sean will talk about some of these later and give another example of how they look. Within coreboot, once you get to the RAM stage, the boot process is then separated into these discrete states that will do different phases of device bring up. This has been redone into a sort of a state machine in the more recent versions of coreboot. And you can then define callbacks when the different states are entered or exit. So this can be a way to sort of interject arbitrary code that needs to be run at a different point in the boot process without having to have a specific device with a driver that is then bound and run. So this is a way to guarantee that you're running at a specific time. So these callbacks are, every time we enter a new state, we look for any callbacks that have been registered for on entry to that state. Those get executed, run the state for the actual work that is done at that boot phase, run the exit handlers, and then go on to the next state. The boot states that are used, that are defined here, as you can see, sort of follow the common things of how devices are then enumerated, resources are assigned, devices might need some special enabling and initialization that is then run at these different stages. And then the common sort of end of firmware things that might happen, we look for an OS resume vector and jump back to the OS if we're happening to resume from S3. Write out different coreboot tables if we're going to boot. So ACPI tables, MP tables, PRQ, all that stuff if you're doing really legacy booting. Then we load a payload out of CBFS, which I'll talk about next, into memory, and then execute that payload. And so you can actually register a callback at any of these different phases. There's a couple of them that are inserted here that don't have any specific actions, but are there to just let you register a callback if you needed to run very early or after all the devices have been brought up. So a very contrived example here, obviously, of how you could hook into the callbacks for before device setup and after device setup and do some sort of magic initialization that may need to happen. So you just define a few functions, and at the bottom of the file you can sort of, this magic macro that you'll see in bootstate.h will allow you to define and state when you want these different functions to be executed. Okay, so I referenced CBFS. CBFS is a simple flash-based file system that coreboot uses. This is something that's been in part of coreboot for a long time now. It has a pointer that lives at the very end of the ROM that sort of gives you an offset to where the actual file system lives. So it kind of has an indirection step to find where CBFS lives. This is to make it so you don't have to actually parse through the entire firmware image to find where your CBFS is. A number of different things are actually stored in CBFS, and coreboot uses this pretty heavily. So the actual boot stages themselves, ROM stage and RAM stage, will actually be separate files within this coreboot file system. Any option ROMs that may be bundled with it will be in here as well, a VGA option ROM or something that doesn't live within the device itself. For systems that, like laptops that might have onboard memory and don't have SPDs, those can actually be bundled up and stored in here as well. Microcode updates is a new thing being put in there, and we use it to put reference code binaries. So if we need to run Intel's memory reference code, that is compiled as a separate standalone binary. It is put into CBFS and pulled out and executed during the boot process. So within coreboot, CBFS has a number of helper functions here. I've listed out a couple of the common ones for booting a different stage, or if you're trying to boot ROM stage, it'll use load stage. If you're trying to boot a payload, you can have a number of different payloads in CBFS, and there are different flags and options to say which payload to boot. And then the common one for things like getting the reference code is this get file content. And here's an example at the end of how we're looking for this mrc.bin that might be in the default CBFS media, and we have a magic tag that we came up with just describes that this is a MRC binary. Now with the outside of coreboot, there's a utility called CBFS tool that allows you to work with the CBFS image that's in the BIOS. And so with this, you can actually, by default, when coreboot is created, it'll have an empty file system here. You can add the stages in, so the build process will add them in automatically for you, RAM stage, ROM stage, and a payload if it's configured at the build system to generate a payload by default. One of the nice things is that it allows you to then change out the payload without having to recompile coreboot. So you can take a BIOS image that's on a running system, pull it off, you can swap out the payload with something that you either has a bug fix or is your own version with debug information, and flash it back without having to change coreboot itself or recompile anything. And that can be very useful for debug and for sort of end users being able to play around with the system. And another example here of how we add the actual microcode binary, and there are some makefile directives that will allow it to be sort of added into the CBFS image by default when coreboot is built. And we use this once again for the reference code binary that we bundle with systems. Another interface that's pretty common and used pretty heavily throughout coreboot is called cbmem. It's a generic runtime memory storage interface as opposed to a flash storage interface. This will have any number of sort of data that's generated at boot time. We've made some extensions to it to keep some additional information that I'll talk about in a second here for event logging, memory console, and timestamps. This cbmem region is reserved in the E820 map, or whatever map is used to describe the memory to the system, so that it isn't overwritten by the OS, but it can be read and stuff can be pulled out of it if it knows how it's formatted. It can also act and function like an UEFI hob. You can sort of have entries that are added in ROM stage and then pull them back out in RAM stage, assuming they're not too big, because we obviously don't have a lot of memory available before memory is available. So it's very simple to use. There's a number of IDs that are defined for different data that might be in there. And generally, I think these IDs map to a hex or an actual string, and these are just the ASCII characters here. Coreboot will initialize this data. It actually will reinitialize it upon entry to RAM stage and upon different points of the boot to get access to the CBMM that may be there that it doesn't know about yet. So when you first jump to a RAM stage image, it actually doesn't know where CBFS is, so it'll reinitialize, find that old pointer, and then sort of regain access to what had been put in there before. To add a new entry, you just give it an ID and tell it how big it is, and you get returned a pointer to your new blob of data in memory. And you can then look up an ID again based on that, or look up a region again based on that same ID. One of the things we use it for is this idea of CBMM console. And this is another thing that we did in the data centers that became useful, was storing a record of all the stuff that would normally be printed on serial into memory, so that when you boot the system, you can actually get access to that log of boot. Obviously, in a static system where it's never going to take any different paths based on things like Chrome OS device, we don't want a lot of variation in how the firmware boots. So this may look the same every time, but it still is useful if for some reason there was an error found, this register didn't contain what we expected, so something went different in the firmware. And so this console output is saved into a memory buffer in CBMM. In the early ROM stage, we actually use a little bit of cache as RAM space for it. Luckily, we don't have too many messages in ROM stage, so we don't have to worry about too much stuff going in there. In very early RAM stage, before we have CBMM reinitialized again, a static buffer is declared and used to store the console data that happens there. And then once we get full RAM stage stuff up, CBMM is reinitialized. We take those other buffers that may exist and sort of put them all together and form the full boot log. Another thing we store in there is a table of timestamps. We have a very big focus on boot time with Chrome OS. It's one of the sort of, that and security were a couple of our major points when we started. We wanted to boot fast and we wanted to be secure doing it. To keep us on our toes, we keep a good strict record of timestamps at boot. And we can then very easily see what different phases the boot process is taking. If for some reason we see that, RAM stage device initialization has suddenly gone to half a second, we can be very concerned about what might be going in there, and it gives some pointer as to where to go look for stuff. Chrome OS in general runs a number of tests and keeps track of boot times across all systems. And having this table allows us to sort of help point the finger back at the kernel if for some reason the boot slowed down or something like that. We can say that, according to our table, we exited the firmware at 600 milliseconds, and yet you're saying that kernel didn't come up until 1.5 seconds. There's some time lost there that probably isn't firmware. So we do try and collect a number of different points with timestamps and save them off. And so you can get at this data at runtime because this memory still exists and is reserved. There's a user space utility called CBMM that lives in the coreboot repository. It can print the memory console. It can get the timestamp table out. It can also get some code coverage information generated with gcov if it's been configured and built with that. And then we have a kernel driver that we wrote for the data center side that actually pulls out the memory console and stuffs it into sysfs. So on any Chromebook, you can log in and look at sys firmware log, and that'll actually contain the complete BIOS boot record of the boot for the system. Obviously, our data center systems use different mechanisms, so this kernel driver does know how to talk to a couple of different, does know how to find this memory log in a couple of different ways depending on the firmware that's being used. This driver's been upstreamed. It's in the main kernel now. I alluded to event logging being very important. This is something that has been extremely useful for us and is another thing that we started doing on the data center side of things at Google and sort of I carried forward into our Chrome devices as well. Obviously, in the data center, we've got lots of machines that sit there with they're headless. Getting the event log out of them is a great way for us to know what happened to those systems. And for Chrome OS devices, they're essentially headless to us because in order to get into them, we have to go to developer mode and a bunch of stuff is wiped and we lose some good information. So by gathering and storing these logs into the flash, we actually guarantee that we have a good copy of it that's in non-volatile state. If the user recovers their system and wipes it, we actually don't lose this log of data unless the firmware was reflashed because it was corrupt. We can also do runtime logging of events. This is, on x86 we use an SMI. We call back into the firmware. It can go and write out a new event log type. This is how we do things on pretty much all the x86 systems. ARM obviously doesn't have SMI, so we use some runtime logging methods that can access the flash directly and write out events. It's a little less, I guess it's a little less flexible and a little less guaranteed that it's going to the event's going to be written, because it's a little harder to know that you can write to flash if for some reason your kernel panicked. You generally don't want to talk to devices, but if you issue an SMI, then the firmware has a different view of the world. Inside the MOSIS utility is the event log parser that can read out and parse this event log and dump it out to the system. And inside the kernel, again, we have a driver that's upstream called GSMI, and it actually initially was written to interface with EFI and a number of different SMI interfaces that are there for reading NVRAM variables and things like that, that we wrote for the data centers and we upstreamed, and then I sort of made use of in the Chrome OS side. And so this hooks into different notifier chains in the kernel. So if the kernel panics or if the kernel's going to go down and reboot, it'll actually send an event and log that into the firmware immediately. And so you can get a great record of the system. I think the next 2 slides will show it here. First, talk about what it looks like within coreboot. Again, kept very simple. There's this elog.h file that defines a number of different functions that are available to sort of log an event of different kinds. And because it's based around the SMBIOS event log, the event log type is fairly small. It's fairly well-defined for some of them, and we use some OEM events to extend it and allow us to describe different things. So as an example, in the links point elog stuff, we read out a register from the ACPI power management area and check for different bits that are set that let us know what happened to the system. So when we're coming back up, great to know what we woke from. Are we coming from S5 or S3? Was there a power button event? We have similar files for the event for the embedded controller. We can read back from the EC what events it may have seen that woke the system, so it can tell us if the user pressed the power button on the EC side. And it can also tell us, we also log a record of whether you're in developer mode or recovery mode, and so that when the user does perhaps submit feedback and says, oh no, I was running verified mode the whole time, I can sort of point at it and say, well, it says you were in developer mode, and then find out who's telling the truth. Here's an example that's sort of been slimmed down to show some details here. When you run MOSIS, it pulls out these events and decodes them and shows this. And so you can see that this particular system opened the lid, it woke up from S5 and booted. We keep track of the boot number, and so you can sort of correlate events back to a boot number, which can be useful. And then we can see that the system went into suspend, woke up later, and it woke up because GPIO 11, which on this particular system happened to be the touchpad, so someone clicked the touchpad and the system woke up. Of course, it looks like when we got back to the kernel panicked and wrote back an event saying it panicked, and the system rebooted again. So if someone submitted feedback, I could tell very easily what happened in this situation. Your system was suspended, woke up with the touchpad, and the kernel panicked. And it gives us some idea of where to go look for perhaps where the problem is. And more importantly for me, it sort of points the finger at the kernel in this case, rather than at the firmware. And that's it for the slides that I have. I do want to mention, I forgot to say this at the start, but there is an alias that I've created at chromium.org that if you mail to will actually reach all of us that are presenting today, and perhaps some other people that I'll add from Chromium team later. And this is not a mailing list, it's more of a reflector. So you email this list, you can email it without having to join, and it'll get to us. That way you can reach us if you have follow-up questions that we may not get to answer today. And we'll be able to respond to you there. So any questions? I do want to point out that there will be future sessions that go into a lot more detail on some of these things at coreboot, so don't feel like this is all you're going to get. But I'm happy to answer any questions about the Chrome OS firmware and coreboot stuff. So initially we actually initially used, oh, sorry, I'll repeat the question. One of the Samsung ARM Chromebook shipped with U-boot, and in fact, the early Chromebooks ARM work we had done was all based around U-boot. Why are we switching to coreboot on those as well? We decided we wanted to have a unified firmware story. There's actually a lot less work needed to boot an ARM system, and so it really isn't that hard for it to be ported to different firmwares. We actually used U-boot on the x86 devices too initially. So in particular, this device here, which is the Samsung Sandy Bridge Chromebook from about 2-3 years ago, this actually boots, instead of Depthcharge, it booted U-boot. And so we had ported U-boot to x86, and it was integrated with verified boot, and we used that. And so initially on x86, we moved away from U-boot for the bootloader because it was sort of too big and unwieldy for what we really needed to do, which was just boot Chrome OS. And then once we had a sort of a solidified story in x86, we've been trying to see what we could do about bringing that to ARM as well. But yeah, they're both good firmwares, and we just happen to have a focus on coreboot. Anyone else?